done with cogging. Now let us see what is crawling. So to understand the concept of crawling, you need to understand the concept of harmonics, because crawling is due to harmonics. Okay, now let us see. I have taken one coil here. This is one coil which has two turns, A and A dash. Okay, so for better understanding, I have cut the periphery like this and I have expanded the periphery like this. So this is my A dash, A, this is my A and A dash coils. Okay, so this is my one coil side, this is another coil side of one coil. So these two will get connected through overhangs. You already know that, right? So now let us see what happened here. This is cross means the direction of current, that is the current going into the plane, and this dot means direction of current that coming out of the plane, means current going into the plane here and coming back from this side. Okay, now let us, by applying right hand thumb rule, Fleming's right hand thumb rule, you can find out the direction of flux, right? So because it is going into the plane, so the direction of flux will be clockwise direction. So the direction of flux will be like this, and so this is the direction of flux, okay, clockwise direction. And what is the direction of flux here? It is coming out of the plane, the current is coming out of the plane, so the direction of flux will be anti-clockwise. This is the direction of flux, so this is like this. Okay, this is clockwise, that is anti-clockwise. So here in between these two, you can see this direction of the magnetic field is same, in the same direction, and after this the direction is upward, and after this also the direction is upward. So I am going to take the graph of these two things here. So for down direction I am taking it as this one, okay. For up direction I am taking the negative thing. So this is the magnetic field that is being produced by one single coil. Okay, now let us see what happens if I have two coils. So this is my another coil B, so this will be my B dash. Okay, these two will be connected through overhangs here. Okay, so you already know that. So let us see, I have connected one more coil, that is B here and here also. So what will be the waveform for that one? That will become like this. So the waveform will be from here up to here. Okay, this is for B coil. Now let me add another coil C. So what will be the flex waveform for this? C dash. So that will become like this. So on, if you keep on increasing the number of slots on the periphery, so what will happen to the MMFs here? So they will be like this. Okay, if you keep on increasing the number of coils on the periphery, so the MMF will be like this. So if we add all these MMF waveforms, so the resultant waveform will be like this. Okay, the resultant waveform will be like this. Like this. So you can see this is the resultant MMF waveform due to all these coils. Okay, so it is not sinusoidal. You can see this is a fundamental sine wave. Okay, but this is a stepped wave. The original one is a stepped wave. This is a stepped wave. I can say the blue color wave due to the MMFs or fluxes in the core are not sinusoidal. These are stepped waves. So actually we want it as a sinusoidal wave because of the harmonics. I can say the term harmonics. So due to the slots here, we are getting a stepped waveform instead of sinusoidal waveform. So these are called space harmonics. And the current through this windings is a DC waveform. It is a DC magnitude. Okay, so for a DC current, the waveform of the MMF is stepped waveform, and it containing some harmonics because it is not a sinusoidal wave. So we can treat any wave not sinusoidal. If this is a sinusoidal, if this is not a sinusoidal, this is a sinusoidal, this is not a sinusoidal. So we can treat it as it is a sinusoidal wave having some harmonics. Okay, so it is a sinusoidal wave having some harmonics. It is a waveform which is having a harmonics. Our pure sinusoidal has no harmonics, but our non-pure waveforms other than sinusoidals are considered to be having harmonics. Okay, so here we have space harmonics in the MMF waveform, and here if I apply AC waveform instead of DC waveform to the windings here, so that will become a standing pulsating waveform. that I am going to explain later. So instead of the sinusoidal wave, what if I apply a waveform like this? That means this red color waveform is having harmonics here, because it is not a sinusoidal wave. So these harmonics are called time harmonics. Time harmonics. So the harmonics due to the spatial distribution of MMF wave are called space harmonics, and the harmonics due to the excitation are called time harmonics. Okay, the space harmonics are related to physical displacement, time harmonics are related to electrical parameter. Okay, so this is about harmonics. The waveforms other than sinusoidal are considered to be having harmonics present in them. So by using Fourier series analysis, we can convert this non-sinusoidal waveform into one fundamental waveform in addition to harmonics. So that is the beauty of harmonics, the Fourier series, right? The beauty of Fourier series is any non-sinusoidal waveform can be converted into one fundamental sinusoidal waveform in addition to number of harmonics. Due to the symmetry of the waveform, due to the symmetry, that means the positive side equal to negative side, this waveform will be absent from even harmonics. Even harmonics are absent for a symmetrical waveform. So this is our MMF waveform due to the space harmonics. Okay, due to the symmetry in the positive and negative side, so this waveform is free from even harmonics. Even harmonics are absent here. Okay, so due to the symmetry of the waveform, the even harmonics are eliminated. And one more thing here, due to we are applying a 3-phase AC voltage to our machine, so the third order harmonics will be eliminated. That means third, sixth, ninth integrals of 3 will be eliminated from the waveform. So we are left, we are absent of the harmonics. Even harmonics are eliminated, 12th, 4th, 6th, and our third order harmonics are eliminated. So we only left with 5th order harmonics and 7th and 11th, 13th, like this. Okay, so we consider the harmonics 5th and 7th as dominant harmonics, because the magnitude of these 5th and 7th harmonics are high due to the rest of the harmonics. So these two will contribute around 60% of harmonics with the respect to the total harmonics. Okay, these two harmonics will contribute 60% of the harmonic content. Okay, so we treat 5th and 7th harmonics as dominant harmonics here. So, and there is one thing here, the harmonics speed can be calculated using a equation like this. Okay, so here m is an integer having values 1, 2, 3, etc. So for m equal to 1, the harmonics will be 6 plus or minus 1, that will become 6 minus 1 and 6 plus 1. Okay, what is 6 minus 1? 5th harmonic and 7th harmonics. If m is equal to 2, this is for m equal to 1. Okay, for m equal to 2, that will become, what is the values? 12 minus 1 will be 11th and 12 plus 1 will be 13th. So this is the order of harmonics here, and you can see here this minus sign, 6 minus 1 sign harmonics are called backward harmonics. Backward harmonics. These harmonics rotate backwards, and 6 plus 1, the plus 1 harmonics will be forward harmonics. The direction is forward. Okay, due to this. Okay, this is about harmonics. 6m minus 1 harmonics will be backward harmonics, the direction is backward, or negative harmonics, or 6m plus 1 harmonics are forward harmonics, or they move forward. That means if the MMF wave in the air gap is rotating in this direction, okay, this is my air gap MMF. So our 6m plus 1 direction will be the same direction of MMF, but 6m minus 1 direction will be opposite to MMF wave. So this is the thing here. Okay, this 6m plus 1 will add up to our rotor air gap MMF, but 6m minus 1 will be opposite to our rotor MMF. Now let us see the torque slip characteristics so that we can conclude the crawling concept. And one more thing here, the speed, the synchronous speed for a fundamental waveform is this one, okay, which is 120 f by p. What is the speed of our 5th order harmonic? For any order harmonic, the speed will become 120 f by n into p. N is the order of harmonics. Okay, for any order harmonic, the speed will become n by 120 f by p. That is nothing but ns by n. Can I write like this? For a 5th order harmonic, what is the speed here? That will become ns by 5. Okay, for a 7th order harmonic, the speed will become ns by 7. That means the speed is reduced by 7 times here, the speed is reduced by 5 times here. Okay, this is one thing to remember. Now let us see the torque slip characteristics. Now let us see the definition for our crawling. Okay, crawling is nothing but, you can assume it as a kid crawling at the age of 7th and 8th months. He can't walk, he crawls on the ground. So that is nothing but a low speed operation. Okay, so crawling is nothing but the squirrel cage induction motor has a tendency to run at very low speeds, okay, compared to its synchronous speed, nearly 1/7 of synchronous speed. So this phenomena is called crawling. That means our squirrel cage induction motor has a tendency to run at very low speed. Okay, this is the tendency of our squirrel cage induction motor to run at very low speed compared to its synchronous speed. The speed is nearly 1/7 of synchronous speed. Okay, the speed is nearly 1/7 of synchronous speed. This phenomena is called crawling. Okay, crawling is nothing but the speed of the machine has been reduced by 1/7 of synchronous speed. So why it is happening? Let us see. So here this is the complete torque slip characteristics of a induction machine. So why I am mentioning machine here? So here we have the operating region for motor, and here this is the operating region for generator. Okay, you can see the operating region for motor is between 0 and 1. The slip value is between 0 and 1. The operation is called motoring mode. And if the slip value is negative, that means less than 0, this region is called generating region. Okay, in this region our machine will act as a generator. Okay, here the region where s greater than 1 is called braking region. Okay, the s is between 1 and 2 here. So this is braking region, motoring region, and generating region of our induction machine. Okay, and this is when our speed is ns here. So let us draw the same characteristics for a fifth harmonic component. Okay, so let us write here, and because it is a fifth harmonic is backward direction and seventh harmonic is forward direction. Okay, that will be left to this point, s equal to 1 point. So that will be like this. This is my fifth harmonic characteristics. Because its magnitude very small and the speed ns is here, it is less than, it is in the order of ns by 5. Okay, and our seventh harmonic characteristics will be like this, and the speed, synchronous speed will be ns by 7. So this is ns, this will be ns by 7. If I treat it as 1400 rpm or 1500 rpm, if my synchronous speed is 1500 rpm, what will be the speed of the seventh harmonic synchronous speed? That will be 1500 by 7, it is around 200. Okay, so you can see this is the harmonic, this is the seventh harmonic characteristics, and this is fifth harmonic characteristics, and this travels backward direction and this travels forward direction, and our electromagnetic torque also is in the forward direction. So our seventh harmonic torque will be added to our electromagnetic torque. Now let us see what is happening here if they are added up. I am going to add the seventh harmonic component because our machine has seventh harmonic component. So thus that will be like this. If I add our seventh harmonic component and fifth harmonic component to our waveform, that will be like this. Okay, so this is the actual waveform with harmonics of our machine. So this is due to fifth harmonic component, and you can see the magnitude of fifth order harmonic is more compared to our seventh order harmonics. Okay, as the magnitude of harmonics as the order of harmonics from 5th to 7th to 11th increases, the magnitude will go on decreases. Okay, for 5th it is more, for 7th it is less, for 9th it will be more less. Okay, so keep on decrease. Now let us see. So I have a torque load characteristics of the machine as like this. This is my load characteristic. This is our electromagnetic characteristics. So our machine runs when our electromagnetic torque is more than load torque. This is the condition, or it should be equal, more than or equal. Equal means it will be stable operating condition, or electromagnetic for running, for starting or for running it is a condition. For stable operating condition it is they should be equal. This is stable. This is for starting. Okay. Now let us start the machine. So this is my starting torque, electromagnetic torque. This is starting. So here electromagnetic torque is more compared to our load torque at the time of starting. So it will be keep on increasing, and our speed of the machine picks up slowly, and it will come to this position. Here you can see this is the point of meeting of our electromagnetic torque. This is electromagnetic torque. Okay, this is my load torque. Here you can see beyond this point our electromagnetic torque is less compared to our load torque, because this is load torque TL, this is my electromagnetic TM, T electromagnetic. So this value is more compared to this value. If this is 10, this will be around 9. That means our electromagnetic torque is less than our load torque here. So the condition to start is electromagnetic torque should be greater than load torque, but here our electromagnetic torque is less than load torque. That means our load torque has locked the machine from running. Okay, our load torque has blocked the rotor from running. That means our machine will decelerate and it comes to this point. That means this will be the speed of the machine. This will be the speed of the machine. Okay. Now our machine stops running here. That means the machine runs at this speed. This new speed is called our synchronous speed of seventh harmonic. That is nothing but ns by 7. I hope you understand. We have added up our seventh harmonic torque slip characteristics to our fundamental torque slip characteristics. So due to that, our load torque has been made by our electromagnetic torque at this position instead of this position. Actually, it has to support, it's supposed to meet the load torque here. This is our full load speed, I can say, but instead it is meeting the load torque here only. Okay, so the electromagnetic torque is less in this region compared to load torque, so it will go back to this stable operating region where our electromagnetic torque will be equal to load torque. So this is the point where our electromagnetic torque equal to load torque. That means this is the running condition, running speed of the machine. That is nothing but this is synchronous switching. So this point is here is ns. So similarly this point here is ns by 7. This is the ns of 7th harmonic. That will become ns by 7. So because of the 7th order harmonic present in the machine, our speed of the machine has been reduced to 7th harmonics. It won't go further because our electromagnetic torque is less compared to our load torque. It can't go further. The speed cannot be increased. That's why it will go back to our electromagnetic torque where electromagnetic torque meet with our load torque. I hope you understand. So instead of meeting the load torque here, our electromagnetic torque has made the load torque here only. So the speed will be like this. That means the speed of the machine has been come to equal to 1 by 7th of synchronous speed. So this is called crawling. Crawling is nothing but the machine runs, but it runs at the speed of ns by 7. That means our machine will run at very low speed, which is nothing but 1 by 7th of synchronous speed due to the presence of 7th harmonic. Okay, this is why we have to eliminate these harmonics. Okay, so how can you eliminate them? I have to eliminate 7th harmonic because it is causing me crawling. So how can you eliminate 7th harmonic? I have in the elimination of harmonics concept in the first unit, I have mentioned you one thing, that using a pitch factor Kp for nth order harmonic, that will be cos times n alpha by 2. Okay, so if you want to eliminate 7th harmonic, this is for nth harmonic. For 7th harmonic, that will be Kp7 equal to cos 7 times alpha by 2. If you make this fraction to 0, if you make Kp7 to equal to 0, the 7th electromagnetic component will be 0. That means if you make this to 0, that means 7 alpha by 2 equal to cos inverse of 0. If you shift the cos to that side, cos inverse of 0 is nothing but 90 degrees. 7 alpha by 2 equal to cos inverse of 0 is 90 degrees here. So 7 alpha will be 180 by 7. So if you make the cording angle equal to 180 by 7, okay, that will eliminate the 7th harmonic from this torque slip characteristics, so that our machine will be free from 7th harmonic and it will be like this. It will be in the earlier case like this. So our electromagnetic torque will be greater compared to load torque until this point. So our machine operates at full load torque, full load speed. So you can eliminate our 7th harmonic by using our pitch factor Kp. So this is the useful thing of pitch factor by pitching the winding. I hope you understand. So our crawling can be eliminated. Crawling can be eliminated by short pitching. By short pitching the winding. Okay, this is the idea. The crawling can be eliminated by short pitching the winding by a fraction of 180 by 7. So this is about crawling. Okay, cogging is nothing but our rotor doesn't starts. Crawling is nothing but our rotor starts, but it will rotate at a less speed compared to synchronous speed. That is nothing but 1/7 of synchronous speed here. So this is about crawling. So cogging can be eliminated by screwing the machine or making the number of slots on the stator not equal to rotor slots or not equal to integral multiple of rotor slots. Here crawling can be eliminated by short pitching the winding by angle this. Okay, I hope you understand the concepts of cogging and crawling. Okay, thank you.